Picture a penalty kick. The shooter has a favorite side, left, and in a vacuum it is the better shot. But the goalkeeper is not frozen scenery. If the same shooter keeps choosing left, the goalkeeper can learn one fact and turn that physical advantage into a strategic weakness. So here's the question. Can deliberately adding randomness produce a better guarantee than always taking the stronger shot? Not always. But in a game where the opponent can best respond, yes, and the probability is not a guess. Use a deliberately small toy model. The kicker can aim left or right. The goalie can dive left or right. Each cell is the kicker's chance of scoring, given those two choices. If both choose left, the score chance is 0.30. Left against a right dive is 0.90. Right against a left dive is 0.70. And right against a right dive is 0.40. These numbers are illustrative, not measurements from a match. They only give us a clean game to solve. Notice the temptation. Against the opposite dive, left is the stronger shot, 0.90 versus 0.70. It looks like left should be the better strategy. Now remove the mystery. If the kicker always chooses left, a goalie who is trying to minimize scoring dives left. The result is only 0.30. If the kicker always chooses right, the goalie dives right, and the result is 0.40. So the better pure action is not judged against a random spectator. It is judged against the response it invites. This is the strategic trap. A fixed policy tells the opponent exactly where to push. Let P mean the probability that the kicker chooses left. Right then happens with probability 1 minus P. Suppose the goalie dives left. The kicker scores 0.30 when left was chosen and 0.70 when right was chosen. The expected score is therefore 0.30 P plus 0.70 times 1 minus P, which simplifies to 0.70 minus 0.40 P. If the goalie dives right, the expected score is 0.90 P plus 0.40 times 1 minus P, or 0.40 plus 0.50 P. These are the two counters the kicker has to defend against. The mix is good only if neither counter can exploit it. The clean way to stop the goalie from preferring one dive is to make the two expected scores equal. Set 0.70 minus 0.40 P equal to 0.40 plus 0.50 P. Subtract 0.40 from both sides. 0.30 minus 0.40 P equals 0.50 P. Add 0.40 P. 0.30 equals 0.90 P. Divide by 0.90, and P equals 1/3. That 1/3 is the turning point. It is not chosen because left is 1/3 good. It is chosen because 1/3 makes the goalie's two counters equally valuable. Plug P equals 1/3 into either line. Both give 17/30ths, about 0.5667. The goalie gets the same expected scoring chance by diving left or right, so switching does not improve the defense. Compare that with the pure policies. A best response can hold always left to 0.30 and always right to 0.40. In this toy game, the mixed policy's worst-case value, 0.5667, is higher than either pure policy's worst case. The qualification matters. If the goalie is not adapting and simply dives at random, left could have a higher average. Randomness is protection against exploitation, not a magic upgrade to the kick. The matrix is ours, but the strategic structure is not. Chiapori, Levitt, and Grosclose describe penalty kicks as a matching penny-style zero-sum game. The kicker wants a goal, the goalie wants to prevent one, and both choose from small, visible action sets. Their study used virtually every penalty kick in the French and Italian elite leagues over 3 years, 459 kicks. The aggregate predictions they could test were consistent with the mixed strategy model. They also found that the current choice of one player did not appear to influence the opponent's current choice, which is compatible with the simultaneous choice assumption. That is field evidence for the mechanism's relevance, not a claim that every player uses our 1/3 number. Real penalty kicks have a middle as well as left and right. Players differ. Scoring probabilities can change with the situation, and the paper explicitly warns that heterogeneity matters. A real model needs real payoffs and a clear assumption about what the opponent knows and when they can respond. So the honest rule is narrower than randomness wins. When an opponent can learn your policy, and the game is close to zero-sum, Choose probabilities that make the opponent's available counters equally good. If those assumptions fail, the conclusion can fail too. Here is the method to carry to another problem. First, write the actions and the payoff in every cell. Second, ask what counter punishes each fixed choice. Third, let P be the probability of one action. Fourth, equalize the opponent's counter payoffs and then verify the resulting value against every counter. That is why randomness can beat a better strategy. Not because chance is stronger than skill, but because unpredictability can remove the opponent's best reply. In our controlled example, the better guarantee is 17/30ths, reached by choosing left 1/3 of the time. The result is conditional, checkable, and useful, which is exactly what a good mathematical strategy should be.